Hello everybody, today I'm going to be showing you my MTRE 3710 Mechatronics Engineering Fundamentals final project. And the requirements for this final project were to make a AVR microcontroller application that involves using interrupts and timers. And so that is what I did. And so what I did, it's not the most creative idea, but it matches the rubric. I made a microcontroller that just controls the state of a motor with an on and an off button. Not really too crazy, but yeah. And so here, this is the code for that, as we can see, and I'll walk through this. So here in the code, we first start by setting the timer to compare timer control timer compare mode, and so this just allows it to be in this mode. That way we are comparing our tick with a variable we set, and when it happens, that's when we trigger an interrupt. Here we're setting that tick, so we set it to the 195th tick, and that's for an equation that I'll talk about later. Time mask is 1 left shifted to the OCIE 0A bit, and this enables interrupts upon timer and the counter 0 output to match. So like when those match, interrupt happens. And then here is setting the prescaler to 1024, and so that is so our clock interrupt is basically interrupting at, I believe it's like 0.99 milliseconds. So I think it's like, I wrote it somewhere up here. Okay, I seem to have lost it. All right, here it is, 1/100th of a second. So a millisecond, I believe. Anyways, so then we do SEI, which sets pin 7 of the S register to 1, so interrupts are enabled. And then here we are EICRA. This is the external interrupt control register, and this sets the int0 and int1 interrupts to generate input requests upon the rising edge of a pulse. Otherwise, if we had it just on any change, it would interrupt twice upon the press of a button. So that's why we want it on a rising edge. And then here is just enabling interrupt requests on int0 and int1. And then this is setting my B pins to outputs where I need them. So that's on pin 0, 2, and 7. And I can show you guys what those are on Proteus in a moment. And then here are my ISRs. So here is int0. So when int0 interrupts, turn the motor off and turn on the emergency light. So this is the off button, int0 pin. And then this the next interrupt is the opposite, turn motor on, turn off emergency light. And then here we have the timer interrupt. And so this interrupt is currently interrupting very fast, and we like that because we want the LED blinking you want to be able to see this LED blinking, because all this is showing you that the system has power. And so this interrupt is just going very fast. However, I have this global variable extra time, and we can use this extra time and self increment it every interrupt, and then we can do an if statement if extra time is equal to this, and then we could make our interrupt last longer without actually having to go to a 16-bit interrupt rather than an 8-bit interrupt, because that's what I'm using. And so this isn't, obviously there are easier ways to do that, but that is just one way I found that you could do that, and it might be useful. I obviously chose not to do that for the speed of what I need blinking, but it is an option. And then here, moving over to Proteus now and centering it. Here is our bus, and we have this set to that file that we were just using, the hex file. We open that, And so if we remember, int1 and int0 was our off, int1 was our on button. So this is our off, this is our on button. And then we had some outputs on PB0, PB2, and PB7. So PB0 is just a red LED that shows that the off button has been pressed if the system is off. Here we have the blinking yellow LED that's from the clock. And then down here we have the green LED that goes to the DC motor and shows that the motor is running. So this is what it looks like when we run this. LED starts blinking as soon as the system starts. That's good. System is running. Let's turn that motor on. Oh, wow. Look at that motor spin. Very nice. And then let's turn it off. I don't like it spinning anymore. Red LED, yellow LED still blinking. So we can see from this small simulation that this system is functioning. So yes, thank you for your time. And as always, go Foxes.